Now, I have a purple plastic stapler that should be somewhere in here, but apparently not.
You're a stapler thief. Stapler robbery.
I don't really have time to go through these today while in class because we've got too much to do. But I will look at it over the next few days and get it back to you. I want to finish 3.2 and move into 3.3. Maybe even finish 3.3. We did that with the two other blocks, so I see no reason why we can't get close to doing that here. How about we start with a cold prayer? So Father, Son, and Holy Spirit, amen. Hail Mary, full of grace, the Lord is with thee. Blessed art thou among women, blessed fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners now and at the hour of our death. Amen. St. Thomas More, so if your phone's not where it should be, could you put it there when I call your name, please? Michaela, Julia, Daniel, the other Daniel, Livia, Samantha, Julian, Claire, Allison, Lauren, Granville, the other Samantha, Brienne, Nicole, Cassandra, Annika, Christina, Decus,
Here.
Alexandria, Annabelle's not here, Mayan, Ariana, Leah. Thank you. So when I handed this out, I said, it almost takes the place. I don't want paper clips, you guys. It almost takes the place of section 3.2, but not entirely. The only thing in section 3.2 that we didn't do is doing the one-step conversion from moles to numbers of items. So that's completely analogous to saying, I got 48 eggs, how many dozen eggs do I have? Or I got 5 dozen eggs, how many eggs do I have? If I got this many moles, how many atoms? Or if I got this many atoms, how many moles? That's all that is. It's not irrelevant, it's just that for macroscopic amounts that I can measure, any chemist knows that the number of atoms, number of ions, number of molecules, number of formula units is going to be ridiculously large. We're not ignoring that conversion, but we're going to bring it into section 3.3. Okay? So if you're interested in moles to numbers or numbers to moles, if you look on page 110 and 111, converting moles to number of items, or converting number of items to moles on page 111. The practice problems at the top of 111 are converting moles to numbers, like dozens to eggs, and the practice problems on the bottom are converting number of items to moles, eggs to dozen, same diff. So look at that if you want to and check your answers, but it's either dividing by 6.02 times 10 to the 23 or multiplying by 6.02 times 10 to the 23. That's all it is. Okay? So if you're going from moles to numbers, notice on the bottom of page 110, you're multiplying by 6 times 10 to the 23. If you're going from number of items to moles, if you look at the sample problem in page 111, you're dividing by 6 times 10 to the 23. That's all it is. So let's move right into 3.3, okay? The questions at the end of 3.2, if you're comfortable with the stuff on the worksheet you did, there's nothing in the 3.2 review that should prove challenging, okay? So let's begin with the top of page 118. I don't really agree with Gary's warm-up there, because whereas you can probably do number 2, you can't do numbers 1 and 3, technically. Numbers 1 and 3 require a little more explanation. So that's what we're gonna do. This is trouble finding my room. Got every other room in the school, just not 224. Unbelievable. Try it again. There we go. Piece of garbage. Now he introduces the wheel model of conversions. We've made a brief reference to it already. We're going to use it a lot more today and going forward. But the wheel model is only a way for you to scope out your calculation sequence, nothing more. If you think you have a better way that gets the right calculation sequence, gets the right answer, fine. This often is a good place to begin, but going forward, you might not need any kind of analogy to figure out your calculation sequence. Look at number 1. Which contains more atoms, 30 grams of chlorine or 15 grams of carbon? Or if you look at number 3, which contains more molecules, 34 grams of methane or 58 grams of oxygen? So remember the ways we represent amounts. We count, we weigh, and we volume. Okay? So here we're given a mass and we've got to go to a number. We can't do that unless we first go to moles. We can't do that unless we first go to moles. And that's a two-step event. We haven't done that yet. But we're going to do two-step and three steps today. Okay? The mole serves as a link between the invisible world of atoms and observable quantities, measurable quantities. Now Gary says the mole is to a chemist what the dollar is to an accountant. Just as the dollar is the central unit of commerce, the mole is the central unit of chemistry. Okay. I would add to this statement. A quantity of one substance can only be related to another quantity of the same or different substances through the mole. So the wheel model of conversions, every chemical species gets its own wheel. And at the center of every one of those wheels is a mole of that chemical species. So we're going to start with just one species, okay? So let's just sketch that out. And let's look at the example he gives us. How many atoms are in 5 grams of copper? Well, copper is our chemical species. We're given a quantity of copper in terms of mass, and we want to convert it to numbers. So we're given grams of copper, and we want to get to atoms of copper. But we can't do that directly. We've got to go through this. Okay? Until we know how many moles that is, we can't convert it to a number. It's a macroscopic amount. In other words, we can measure that. So if we can measure that amount, then we expect that this is going to be a scary big number of atoms. So we expect the exponent to be big and positive. Okay? So that's step 1. That's step 2. So all we do now is write that out horizontally. That's the purpose of the wheel. We first have to convert grams copper to moles copper. And then we're going to convert moles copper to atoms copper. want grams to cancel, it goes here. If we want moles copper to cancel, it goes here. Same as we've been doing since September. Get rid of the arrows. Put in some multiplication symbols. Moles to grams, grams to moles, that's periodic. So if you look at periodic table in the back of your book, the mole of copper is 63.55 grams. In a mole of anything, we have 6.02 times 10 to the 22. Okay? So 6.02 times 10 to the 23. Now that's to 3 sig figs. That's to 4, but we're given 2. So we have to round our answer to 2 sig figs. Grams copper cancels, moles copper cancels. How many atoms does that represent? Well, again, look at, we got that on the top. So we expect this to be a big number. 5 divided by 63 is a little less than a 12th. So we're gonna have a little less than 1/12 of 6.02 times 10 to the 23. And if you look at the solution over here, in terms of guesstimating the size, yeah, that makes sense. 4.7 times 10 to the 22. We expect it to be a really big number because we have our measurable amount, right? Makes sense? Now, in the same way that we could go from grams to atoms, we could go from atoms to grams. Look at what Gary asked us here in the second sample plot. What's the mass of an oxygen atom in grams? Well, we have oxygen, so we're going to put moles oxygen at the center of the wheel. And we're going to go exactly in the opposite direction. Rather than a mass to a number, we're going to start with a number and go to a mass. So moles oxygen goes here. We're going to start with an atom of oxygen. That's a number. And we want to know how many grams it is. Now, when we talked about relative mass, we said any atom is far too small to use grams, and it is. That's why it's a relative mass. So when we say 16.00, that means 16.00 atomic mass units is the relative mass of an oxygen atom, as long as we understand what 1 atomic mass is. But to get 16 grams of oxygen, we need a mole of oxygen atoms. What if we just had 1 oxygen atom? What would be the mass in grams? So this number we expect to be really, really tiny. So we have to find out how many moles 1 atom actually is. And then from there, we convert it to grams. Exactly the opposite direction. So let's write that out horizontally. 1 atom of oxygen. How many moles is just 1? And then how many grams is that? And don't try to figure it out in your head. Just let the units guide you to tell you where the numbers go. So atoms of oxygen goes here. Moles of oxygen goes here. And all we're doing is using this to scope out our sequence. So, in a mole of oxygen, in a mole of anything, felt pens, eggs, garden peas, you have 6.02 times 10 to the 23. So now that number is on the bottom. This is periodic table. In a mole of oxygen, we have 16.00 grams. Now, that's a number, so it's not a measurement. That's got 4 sig figs, that's got 3. So our answer should be 3, okay? So atoms, oxygen cancels, moles, oxygen cancels. Mathematically, we're going 16 divided by 6.02 times 10 to the 23. And that's grams oxygen in 1 atom. And as you expect, yeah, that's a pretty tiny amount. 2.66 times 10 to the minus 23 grams in 1 atom. There's no scale on the planet that will ever be able to measure that level of precision. But we can still calculate, right? Make sense? Now what if instead of that, where we got 1 chemical species, what if we got 2 chemical species? Remember the first page that you guys did in the worksheet? In a mole of carbon dioxide, you got 2 moles of oxygen, right? That's what Gary meant when he says here, a quantity of a substance can only be related to another quantity through the mole. So, let's see if we can put 2 chemical species together. Instead of, if I got this many molecules of carbon dioxide, how many grams of carbon dioxide do I have? What if I said I got this mass of carbon dioxide, what mass of oxygen do I have? Or in this mass of carbon dioxide, how many oxygen atoms do I have? Now we're comparing 2 different chemical species. Before we move to that though, I just want to make sure you guys are okay with this. Don't worry about number 1. I'm never going to give you that, ever. But number 2 is the same as the first sample problem that we just did with the copper. And number 3 is the same as the second one that we did on the board. So do number 2 for me. Do it exactly the same way. How many atoms of copper are in 5 grams of copper? How many atoms of bromine are in 2.1 grams of bromine? We'll leave this wheel up there. And to the extent you're able, pretend you're writing a test. You're going to have your periodic table, your table of ions, and your calculator, and your mind. Okay? So, moles of bromine goes in the middle. Take it from there. And by the way, I don't need to see wheels and stuff on a test. I would just need to see the final answer. The wheels is only to get you the calculation sequence. Get it right? This one you expect to be really big. This one you expect to be really small, correct? This is identical to the second sample problem, that's identical to the first. And don't forget to put in units. This is going to be grams, and that's just going to be a big number, atoms, okay? In this scenario, the 6.02 times 10 to the 23 is on the top. And this one, the 6.02 times 10 to the 23 is on the bottom. And that's why the number is so small. Okay? Something I should probably remind you of, the calculator you're going to use on tests should be the same calculator you're using in class and taking at home. Some of you might be used to using programmable calculators, which is fine in class, you just can't use it on a test. And you don't want to try to figure out how to use the exponent function on a calculator you've never used before when you're writing a test, because you don't have time. And if you're using the exponent function, the EXP button, when you push that, that is doing times 10 to the 40. So don't do something 6.02 times 10 and then put the exponent button, because you're going to be out by a factor of 10. All right? But again, it's get comfortable with the calculator that you're using the test in class and at home. Yeah. And as is always the case, for every question you do, check the answer before you do another one. That way, if you're doing it wrong, you don't do 7 or 8 of them wrong and then find out you wasted your time. Any issues with number 2? You guys get the right answer? If you haven't checked your answer, then what are you doing? This should not take a long time at all. Grams bromine to moles bromine to atoms bromine. Okay? Exactly the way we did for the first one. Grams bromine. Okay? Moles. That's periodic table, 79.9 grams. That's number of atoms. All right? I'm not going to do it for you. I did the other one for you. 2 sig figs. The QR codes in the front side of the second last page in your book gives you the answer to everything. If you haven't checked it, I don't know why, this should not have taken you any more than about 5 or 6 minutes. You've got 2.1 grams of bromine, that's about 1/40th of a mole, because a mole is about 80 grams. So if you've got about 1/40th of a mole, that's about 1/40th of 6.02 times 10 to the 23. It's still going to be a really big answer, real big number, but whatever fraction of a mole is the fraction of 6 times 10 to the 23. And you'd want that answer to 2 sig figs. Okay. What's the mass in grams of 1 atom of silver? Silver has a molar mass of about 107.9. So that divided by 6.02 times 10 to the 23 is going to give you the mass in grams. And that's going to be the 3 sig figs. That'll be a really small number. That'll be a really big number. Okay. I want to move on now. Chemists often relate a quantity of one chemical substance to a quantity of another. That's true. But this word doesn't apply in this context. Stoichiometry is a branch of chemistry that deals with the quantitative relationships between chemical substances involved in chemical reactions. So I had never heard that term before, nor had Sherry, nor had Meg. The word stoichiometry really just means one thing. You don't need to worry about that word yet. But when we get to doing chemical reaction, then we're in chapter 4. So if you look on page, and again, you don't need to worry about this yet, but if you look on page 201, Sherry wrote chapter 4. Calculating with chemical change, that's stoichiometry. So just because Sherry needed to remind everybody that this isn't really what stoichiometry refers to, composition of an individual compound. She said, in the mole chapter, stoichiometry was introduced through the quantitative relationships between the elements in the chemical compound. It is far more common, which is her way of saying we don't use stoichiometry in this context, to use stoichiometry to study the relationships between various elements and compounds involved in chemical reactions. That's stoichiometry. So this isn't really stoichiometry. So we don't have to call it anything to know what we're doing. Okay? And then he goes into what the word comes from, it doesn't matter. A quantity of a substance or species can only be related to another through the mole. Every chemical species gets its own wheel. And at the center of every wheel is a mole of that chemical species. And in the same way, the two wheels can only be connected with an axle, connecting the center of each wheel to each other. If the center of the wheel, if each wheel is a mole, then moles is the only way you can do it. And you guys did this on page 1. In 1 mole of carbon dioxide, I got 2 moles of oxygen. That's all we're doing here. Okay? So the best way to go through this is just start with an example. Let's start with this one. How many moles of methane are required to get 0.860 grams of hydrogen? So there's one chemical species, there's the other, correct? So that means 2 wheels. 2 chemical species, 2 wheels. So there's 1 wheel, there's another one. The quantity we start with is the first wheel. So we've got a mass of hydrogen. So let's put moles of hydrogen here. And we're using that quantity to get to this quantity. So we'll put moles of methane here. Now we look at the question again. What quantity of hydrogen are we given? We're given grams. Grams hydrogen. We want to know with that mass of hydrogen, how many moles of this are we going to need to get that? Well, just connect them with arrows. This is step 1. Grams to moles, moles to grams, that's always a periodic table. This is just the chemical formula. Correct? That's step 2. And you guys did that again on page 1. In 1 mole of methane, how many moles of hydrogen? 4. That's the connection, okay? So we're going to go grams hydrogen to moles hydrogen. That's per our diagram. That's periodic table. Moles hydrogen to moles methane. That's chemical formula. Grams hydrogen goes here. Moles hydrogen goes here. All we're doing is writing that out horizontally. So according to periodic table, and now we use our periodic table at 2 decimal places. 1.01 grams of hydrogen in a mole. This is just chemical formula. In 1 mole of these, I got 4 moles of those. What mass of hydrogen do I start with? 0.860. Now, if 1 gram of hydrogen is a mole, and I got 0.86 grams, then I got about 0.86 moles. Time divided by 4 is about a little more than a quarter of a mole. Okay? So, make sure the units work. Grams, cancel, cancel. Now, Gary uses 1.0 grams. But that answer makes perfect sense. 0.860 divided by 1 is 0.86 moles. 0.86 moles divided by 4 is 0.22. Now, we could have gone farther than that. We could have said, what mass of methane is needed to get 0.86 grams of hydrogen? So if we got this, we could go to grams if we wanted to. Or we could have gone to molecules of methane. We could have done that too. Once we get this, we can do a whole bunch of stuff. Does that reasoning make sense? Now, this almost overcomplicates it. That you probably could have figured out already. And I don't need to see this ever on a test. I just need to see that. However you get to it is up to you. Okay? Let's look at a sample. Let's see what it does here. So this is now a three-step event. How many grams of oxygen are in 14.6 grams of carbon dioxide? Well, oxygen is one chemical species, grams of carbon dioxide is another, so we need two wheels. The quantity you start with is associated with carbon dioxide, so that's our first wheel, moles CO2. And we want to know how many grams of oxygen. So moles oxygen goes here, that's our second chemical species. We're given grams of CO2. We use our periodic table to get how many moles that is. We use our chemical formula to go to moles oxygen. And then we use our periodic table again to get to grams oxygen. So the purpose behind that is just your sequence. Now write it out. Grams carbon dioxide. Step 1 goes to moles carbon dioxide. That's what you guys did on the worksheet. Moles of carbon dioxide to moles oxygen. You did that in the first page of the worksheet. Moles of oxygen to grams oxygen. Again, worksheet. Make the units work. Grams CO2 goes here. Moles CO2 goes here. Moles oxygen goes here. We've been doing this since September. Get rid of the arrows. Put in multiplication signs, put in the numbers. If you go by 2 sig figs in our, or 2 decimal places in our periodic table, I think you have 44.01 grams per mole. In a mole of CO2, I got 2 moles of oxygen. It's like a mole of bicycles. I got 2 moles of wheels. And this is periodic table. And what do we start with? 3 sig figs. So we'll do the math. Grams cancels, moles cancels. Grams of oxygen should be 2 3 sig figs, all right? And this is a simple problem, so he does it for you. 10.6. Let's look at some practice problems. Look at number 1. That's page 1 on your worksheet, right? In a mole of SO2, 2 moles of oxygen. In a mole of C2H4, 4 moles of oxygen. Or so 4 moles of hydrogen. Look at number 3. And again, I'd never give you all that. So what might I do to make number 3 look like a test question? How about how many oxygen atoms exist in 2.5 grams of potassium dichromate. So I might not give you the formula, I might just give you the name. And you already know from doing your worksheet that if the formula is wrong, pretty much everything else you calculate is gonna be wrong too. So let's kind of do it the same way we did this one. There's two chemical species you see, oxygen and potassium bichromate. So you know you're gonna need two wheels. The quantity you're given is potassium bichromate, so let's start there. Moles potassium dichromate. And we want to know quantity of oxygen now, okay? So moles oxygen. Now we read it again. What quantity are we given? What quantity do we want to end up with? Well, we're given grams of potassium dichromate. Ultimately, we want to convert that into number of atoms of oxygen. But we can't go directly from there to there. We first have to go to moles. That's going to be periodic table. Then we're going to use the chemical formula to get to moles oxygen. So in other words, however many moles of this that equals, we're going to have 7 times that many moles of oxygen from the formula. And then however many moles of oxygen that is, we're going to then convert that to numbers using the number. So, without me writing it out for you, see if you can take it from here. And you want your answer to be the 2 sig figs. Not to overstress you, but pretend you're doing this at home in your room with you and your calculator and your periodic table and your table of lines, or better yet, pretend you're writing a test. All we did here is, okay, 2 chemical species, 2 wheels, moles at the center of each. Where do I start? Where do I have to get? Scope out your sequence. Turn those arrows into a horizontal sequence. Now, you guys remember when I gave you this worksheet, I said, gee, that makes a great test question, which means that makes a great test question. But one of the things on here is you have to calculate molar mass, remember, in 1 mole of. So would you have to do that for this question? In other words, when you get your molar mass, do I need to see in 1 mole of potassium dichromate? No, I wouldn't, because you're already showing me here. Obviously, I need the molar mass to be correct, but you don't have to show me doing it, okay? So see if you can take,
Yeah.
how hard is it?
Not bad.
Right, the calculation of it looks hard. So, once you get the molar mass potassium dichromate, the rest is just pretty straightforward. Now, if I gave you that, obviously, you gotta get this. If you don't have that, everything else is wrong. So keep that in mind. That's gonna become increasingly important, especially when we start talking about chemical reactions. What about number 4? What mass of sodium ions is contained in 1.23 times 10 to the 24 formula units of sodium sulfide? What are formula units? Why not just use molecules? Why wouldn't Gary say molecule of sodium sulfide? What type of compound is sodium sulfide? Covalent or ionic? Ionic. Any compound that starts with an alkali metal is ionic, 100% of the time. Are there any molecules in ionic compound? No. So that's why he's using fluorine. So you got that many of Na2S. What's the mass of the sodium ions in that many sodium sulfides? So once again, two chemical species, okay? You don't have to do any of these in your head, but why did he pick 1.23 times 10 to the 24? Well, Avogadro's number is 6 times 10 to the 23. And he's picked 12 point something times 10 to the 23. So that's a little more than 2 moles. Now, you don't have to determine that right away, but you will when you start doing the arithmetic. So we're given some quantity of sodium sulfide. And we want to know what mass of sodium ions. Now don't worry if it's a sodium ion. A sodium ion and a sodium atom weigh the same thing because electrons are virtually massless. So we start with a number of formula units, which is just how we refer to ionic compounds instead of molecules. So let's just write the sequence up. This has to be step 1. This is step 2. That's step 3. This is Avogadro's number. This is chemical formulas. That's molar mass. That's periodic table. So, formula units Na2S. Moles. Moles Na2S. Mole sodium. This is chemical formula. Mole sodium. Grams of. That's all that is about. Just getting this. Once you have that, you don't need that. Okay. Formula units goes here. Moles goes here, just like we've been doing since September. Mole sodium goes here. So we have 1.23 times 10 to the 24, or if you want 12.3 times 10 to the 23, which is a little more than 2 moles, because in 1 mole, you have 6 times 10 to the 23. In a mole of Na2S, you got 2 moles of sodium. That's page 1 of your worksheet. And in a mole of sodium, you have 22.99. And then let's just make sure the units work. And again, we don't have to do it in our head, but can we guesstimate an answer? Well, that's 12.3 times 10 to the 23 divided by 6 times 10 to the 23. So that's a little more than 2 moles. A little more than 2 times 2 is a little more than 4. And if 1 mole has a mass of about 23 grams, we're going to be a little more than 4 times 23. So 4 times 23 is 92. A little more than that, maybe 93, give or take, grams of sodium, right? And we want it to 3 sig phase. Based on that, and this, those are exact numbers, so we don't have to worry about that. They're counted. So I would guesstimate 93 point something grams of sodium. But do it and check your answer. What'd you get? 90, 94.0?
Oh, I didn't have brackets.
Now that, again, that looks difficult, walking in the room and looking at it, but it's not. That's the last question in this section, literally. Now, I don't usually do activities, and we don't have time to do the activity today, but we will do it next class. The evaporation rate of water. So what I'm gonna do next class, I'll take a Petri dish, and I'll put water in it and I'll weigh it. And then I'll just put it over there, put it on my desk, and we'll record the mass when I weigh it the first time, and then I'm gonna wait 30 minutes, and then we're gonna weigh it again. It's not gonna weigh that much less, but it will weigh less because oxygen will have evaporated from the surface of the water in the Petri dish. And then we're gonna calculate how many molecules per second came off that water. What's the evaporation rate of molecules per second? The mass difference is not that amazing, but the molecules per second are. And Gary says that. Very bottom of 123. Be suitably amazed. Oh, come on. More amazed than that. Now that sounds corny, but you might be surprised how many molecules per second come off that surface. And I'm going to use a big Petri dish with a big surface area. So we're going to maximize the evaporation. And in terms of the actual scale differences to the nearest 0.01 grams, it's not going to be amazing at all. But when we convert it to molecules per second, it will. All right? But I'm not going to do that yet because we need a whole half hour and we don't have it. Yeah. Now, there are a plethora of review questions at the end of 3.3. You don't have to do all of them, but try a variety. Try a variety of maybe 3-step questions. Maybe grams of one species to number of atoms or molecules of another, or numbers to a mass, or mass to mass, where you use 2 wheels and connect the center of each wheel through moles of each. And don't do 8 and then wait till your 8th answer to check all of them. Because then if they're all wrong, then 7 of those was a waste of time. Do one, check your answer, one at a time. You don't have to do all of them. But if you can do a variety of a few of them, then you're good. And again, remember why I give homework. For you to find out if you know what you're doing, or for you to find out you don't. If you don't know what you're doing, if you can't get a right answer, then that's what we need to talk about on Wednesday. But if every time you do these, doing it this way, you get a right answer, you're good. Yeah. So you can start now. You've got some time. You got over 15 minutes. So pick ones maybe that look similar to what we just did. .02 times 10 to the 23 is a measurement, but you're multiplying by something that's fewer than 3, and you round to that. Okay?